Good morning, everyone. It's a real pleasure to be here. I would like to thank Professor Shi and others for the invitation to share with you some of the research that I've been doing for some time. So what I'm going to talk about is the accumulation of several projects. So I will be talking about resiliency. We get into details of that as how we can move things up a little bit and do things better. I don't think I need to convince this group how important bridges are. But this is just an example. This shows the San Francisco Bay Area. The red lines that you see here, these are the major fault lines in the San Francisco Bay Area. And all the dots that you see, these are the bridges. Functionality of these bridges is extremely important, especially in light of the fact that we have high seismic areas, very active faults. So this functionality is something that you're going to see that we have some issues after major earthquakes. So what is our seismic performance objective? How do we design? What's the philosophy? What are we trying to do in our design codes, seismic design codes? And I'm talking about standard bridges, which by far, there are more than 95% of bridges are considered to be standard bridges, as opposed to signature bridges. So our goal is no collapse. We are saving lives, that's all. But with the understanding that the bridges could be severely damaged and not remain functional. So let's go back to this one. Just think about even a subset of these bridges, if they're not functional after the earthquake, that whole area is going to come to a standstill. And because of the interconnectivity that we have, there are ports here, all the products coming from overseas, everything is going to come to a halt and will affect the rest of the country as well. So it is something very important, the fact that we are accepting substantial damage and the fact that bridges will not be replaceable. So our definition, we are all engineers or material scientists, right? Our definition of failure and success, according to our seismic design codes, are this. If you look at the bottom figure on the left, that's a bridge that was subjected to 94 earthquake. It did not collapse. So it met the design objective, right? But this is how the bridge looks like. You definitely have to shut it down to traffic, and it's not usable anymore. Now, failure is the one on the right side. This is the one that we have a bridge column here, believe it or not. It has completely failed, and this is the superstructure that has fallen. So this is a design failure, but this is considered a design success. And that's something that obviously the public will have a hard time understanding and accepting that yeah, this is not successful. This is bad engineering. This is what they're going to tell us. So what if we go back and rethink our basic design philosophy that we have in our codes? Maybe no collapse is not enough, is only partial success. So we should also look at serviceability after earthquakes. What are the issues? What are the seismic damage that you get? What are the things that we have to deal with? Well, there are two things that happen during a strong earthquake. One is permanent drift that makes a bridge unusable. The other one is damage to plastic hinges, to critical parts of the columns, etc., etc. So how do we address that? How do we try to address these two issues? Well, there are a number of ways we can work with that. One is performance-based design, and we do use that in signature bridges. Again, there are by far the minority of bridges, but signature bridges. We might try to use base isolation to keep the bridges functional, or we may go to advanced materials of different types and different styles and different detail, try to address this serviceability after the earthquake. So if you look at the resiliency curve that you have seen many times, that red zone is what we're trying to avoid. The red zone is trying to either minimize it or avoid so that we can, again, keep the hybrid network functional. Now, let's talk about earthquake damage. And I say new bridges, but because I just want to make sure we are not covering about substandard bridges that need to be retrofitted and all of that. No, I'm talking about the bridges that we design now and build now. So these are the bridges in the past 20 years. We're pretty much meeting all the code objectives. So we have plastic hinge damage and permanent drift. These are the two main issues that make bridges unusable. So this is how plastic hinge damage looks like. Usually at the ends of the columns, that's where the maximum moment is. And we have the cyclic effect of the earthquake. So going back and forth. And the other one is the permanent drift. So after the Kobe earthquake, a lot of bridges, about 100 bridges were tore down because of the permanent drift. If you looked at the damage in the columns, they were not that severe, but they were tilted. And because of that, people didn't feel safe to use these bridges. So they shut them down. So we have to, in order to keep bridges serviceable, there are these two things that we have to address. The plastic hinge damage, control that, and the permanent drift, try to avoid that. Now, let's talk about the plastic hinge damage. What's causing plastic hinge damage in conventional reinforced concrete bridge columns? Well, concrete by itself is a brittle material, unless you help it with confinement and all of that. So what happens is that, let's say if you take a bridge column and begin to cycle the load to simulate the earthquake, in the beginning, you have some cracks in the plastic hinge area. As we increase the amplitude, there is more cracking and spalling of concrete that you get. This will continue, and at some point you begin to have exposed reinforcement. And then eventually you have fracture of the bars. So that's how we end up with plastic hinge damage. It's a low ductility of concrete, and especially the surface concrete, but even the confined concrete at some point where we steel ruptures, then concrete itself will fail as well. So we have failure. So these are the cause of plastic hinge damage. How about the main cause of permanent drift? How do we get that? Well, for conventional construction of steel and concrete, the problem is with the steel. Well, steel is a ductile material. So if you look at the stress strain diagram for steel, under strong earthquakes, we are going to have substantial yielding. However, when the earthquake stops, we end up with this permanent strain. And that permanent strain translates into a permanent drift. And that's when, the bridge is tilted towards one direction, then it's not usable. It doesn't feel safe, even for ambulances and a variety of emergency response vehicles. So how do we deal with plastic hinge damage? How can we reduce it? There are different ways that we can deal with. The use of what is called ECC is basically a grout that has fibers, okay? Fancy name, engineered cementitious composite. So it's a mouthful, but that's what it is. Or UHPC, this is ultra high performance. If this is where you have the steel fibers, it's possible to use elastomeric rubber material in the plastic hinge area. That's the idea, came from Professor Kawashima in Japan some time ago. Fiber reinforced polymers are also a material that can be used to help. So with ECC, this has a nickname of bendable concrete. So this is a sample where there is no steel in there, just the fibers and polyvinyl fibers and the grout. So this is the rubber I was talking about. The UHPC, we get very high compression strength, but it's able to maintain some level of compressive capacity under large strains, also has high tensile strength. And composites also, they can provide or minimize plastic hinge damage. So a couple of samples of these you can see here. Here again. Yeah. So this is where we have a UHPC with a plastic hinge of a column. And we subjected that to shake table testing. This particular run was twice the design level. And you notice there isn't much damage within the plastic hinge. During this run, we fractured. We keep testing until there's failure. But the design level, there was no issue at all. Even at about 175% of design level, there was no issue. Or in this case, we have this is the composite. This was part of a 4-span bridge model that we tested in the lab. Again, under very large earthquakes, it performed well. Did not show any sign of damage. So that there are ways to try to deal with that, controlling plastic hinge damage. How about reducing permanent drift? How do we do that? There are different ways of doing that. There's post-tensioning columns with steel tendons. We could use carbon fiber reinforced plastic tendons or iron-based shape memory alloy. This is completely new concept. We just got a new grant to work on that. Doing that at the University of California, University of Southern California. So that's one option. Super elastic shape memory alloys, nickel titanium. There's copper-based shape memory alloy that are emerging. Again, we got a new project working on that as well, and iron-based ones as well. Also, fiber reinforced polymer composite can help reduce the permanent drift. Now, so if you look at let's say lateral force versus lateral drift, the recentering that we're providing means that when the load goes to zero, so does the displacement. Okay, and that means that after the earthquake, the bridge goes back to its original place or nearly so. So these are the CFRP tendons we have used in some projects. Now, what makes shape memory alloy, super elastic shape memory alloy effective is that if you look at the stress strain diagram, you get this flag shape response. Unlike steel, that after yielding, once we remove the stress, it follows, the curve follows a path that gives us a permanent strain in this area. With the shape memory alloys, super elastic shape memory alloys, the path is like a flag. That means it comes back here. And once the stress goes to zero, the strain is also zero on this material. So these are the kind of things that could help us reduce that. And through many projects, we have already evaluated that. Single columns, multi-span bridges inside the lab, and the lab analytical work that we have done. We have shown that, yes, it's possible to do that. These are some samples. This is where we have CFRP, PT column. The fact that you have the cluster of the curves coming here, that tells you that this is, so we didn't get that much permanent drift at the end of the earthquake. In this case, we're using copper-based shape memory alloy, much cheaper than nickel titanium. And again, it's coming to the origin. The curve comes through the origin, and we essentially have this flagship response. When we use FRP tube, again, we are able to bring things back to the origin, so not much permanent drift. So these have been proven through various projects that can be effective. Now, there is another type of shape memory alloy. This is an iron-based shape memory alloy, much cheaper than other types of shape memory alloy, but still there's a special one. It is heat sensitive. It's temperature dependent. So I'm going to show you this is a bar, which is heat sensitive shape memory alloy, iron-based, and we turned it into an S shape, but this bar remembers that it was almost straight before. So when we apply heat, it tries to go back to its original shape. So it's just sitting there waiting for some hot water to be poured in the dish. And look what happens when we pour the hot water in that dish. Magic, huh? It's the kind of thing that we can also tap into. And we did that in one project, one we tested early last year, I believe, at the UNR. And we built a large scale, that was ABC precast column. And we used these bars, FESMA bars, the central bar, for recentering. And it turned out to be that it was effective. And so this is the elevation of the column that we use. It's, it's a large scale column and ABC, so it's dropped into a socket connection over here. We had the central FESMA bar. Here I'm showing you the lateral drift ratio versus time for different earthquake runs. So we started with small earthquakes, gradually increased the intensity of the earthquake. So the different runs. And you notice that even up to about 4% maximum drift, the deviation from the baseline was minimal. That means that there is no permanent displacement. Okay, that means permanent displacement was extremely small. This trend continued until we fractured the FESMA bar. So during this run, we fractured the FESMA bars. And once that happens, then the deviation, which indicates permanent drift, began to increase substantially because we put a very strong, very demanding earthquake that would cause, this is a near fault earthquake that would cause large displacement. So it was very effective, that worked. Also using with the shape memoryallo and nickel titanium, these are some samples of, let's say here I'm showing you two columns. One is a conventional column, and this is the one that we use shape memoryallo in combination with ECC. So after 10% drift, this is how the conventional column looks like, and this is how the nitinol ECC column looks like. Again, this is very repairable. There are some cracks at the base, very repairable, and because there is no permanent drift, we can continue using the bridge, especially after the seismic loading, after the strong earthquake. You could have fires, you could have injuries, the ambulances, the fire trucks, they all need that bridge. So with this detail, we can use that. And just to quantify that here, in this particular project, we used 3 columns. Actually, I'm only showing you 2. So I'm showing you residual drift ratio versus the maximum drift that we applied. For a conventional column, that residual drift keeps going up. That you see, this is a conventional reinforced concrete column. But when we use shape memoryallo, especially when we use it in combination with ECC, this the permanent drift was about 1/6 of what we had in the conventional column. So was very, very effective. Again, the case where we're using UHPC and CFRP tendons after the earthquake, this is how a conventional column looks like, but with PT alone, without really doing ECC or UHPC. But this is where we use CFRP tendons and UHPC. So indeed was effective. Now, is this a dream or reality? Well, I'm pleased to tell you that it's not, but we're certainly a few steps closer to reality than just a dream. Why? A few years ago, I did a project, my team funded by NCHRP, where we developed guidelines that anybody who comes up with these new novel details, how they would evaluate them. So we developed these guidelines. We took some of the select details and showed there are 5 or 6 design examples in this document. And this document is available for free, can be downloaded. And those of you who have worked with NCHRP know that NCHRP is actually a technology transfer tool, okay? And decisions are made by engineers to fund the project or not. And the fact that there are enough progressive engineers wanted to know how we can utilize these advanced materials, I think is very, very promising. And just to show you that that's even more promising, the fact that we have used and implemented one of these details in a bridge in downtown Seattle. This is an off-ramp structure, 3-span bridge, Alaska Way viaduct replacement in Seattle, but they totally changed the whole setting there. So 3-span bridge, 180 feet in the middle, 110 on the sides, single square columns. Now, to optimize this using shape memory alloy, nickel titanium, and ECC, we did some research specific to this bridge. So we built models of the columns of this bridge. We had one conventional one and two other ones with different length of shape memory alloy. So this is the long, this is the one with the long one. And by long, I'm talking about the length was equal to the side dimension of the column. So it's not that goes over the entire length of a column. And we said, well, what if we reduce that to 75% of the dimension of the column, the length of the SMA bar? And even that, we gave us 10% drift capacity, which was excellent. Even at 10%, you see very little damage. So it was demonstrated for the columns mimicking the columns of this bridge. We were able to, again, accomplish good response. The end result was that in the actual bridge, we used 80% of the side dimension. So as a result of this research, we found that is effective. And these are force displacement relationship, lateral force versus displacement relationships. For the conventional column, it was a well-designed column, right? Met current codes for conventional columns. So we had good energy dissipation, excuse me, and good response. But for the other two, where we had shape memory alloy, we had good response, but flag-shaped response. That means there is no permanent or very little permanent drift. And to quantify that for you is looking at the residual drift ratio here versus the drift. These are the two that had shape memory alloy and ECC. This is the conventional column. So we had large residual drift, even under 4% drift, we had about 2% residual drift. So certainly, the effectiveness of shape memory alloy, that combination was shown. And of course, then we applied that in the bridge. So this is a cross-section of the bridge. And this is extended column. So we use the material only in the top plastic hinge of the column. So, and some details of that, these are large diameter bars that are the 30 millimeter bar, almost like number 10, with 10 bars. And to minimize the waste, we use this standard couplers, HRC couplers, and connected the bars to steel bars. Now, for the quantity that we use in the bridge, the price was about $90 a pound. But for smaller quantities, I guess they charge you more. Chris tells me that now they have raised the price because of inflation and all of that. But this was done successfully in the field. This is the column cage. On the top plastic hinge, we have these couplers. And so the yellow bars are the nickel titanium bars. So they were connected to steel bars at the top, steel bars at the bottom through these standard couplers, HRC couplers. So this is a bridge under construction, and then the completed bridge is shown over here, and the bridge is done. It was about 2.5 years ago, it came on service. And this project won a lot of awards, and I'm not showing these awards to brag. I'm going to make a point from these awards. These awards are for, I guess there was a fifth one, I don't know which one. But the selection of this project for the awards was done by practicing engineers, okay? That's very important because, again, it shows that there are enough engineers who say, well, let's look at things differently, okay? This one was a journal paper. Okay, so this one you say, yeah, your peers selected that. Okay, fine. But these other ones where selection was done by practicing engineers, and that was very, very encouraging. Now let's move to the future. This is futuristic enough. So what does the future hold for us? Now let's talk about human psychology and how we live. We are very good at predicting what to expect in the future. Okay, we have some visions, some thoughts. We're very good at it. We are terrible when it comes to predicting how we are going to get there. So the what part is okay. The how part, we don't do a good job. A good example of that, this is how we said, well, where people say someday human being will be able to fly. Yes, absolutely. So this was the what part. But the how part was this, right? So we thought, well, yeah, we can put a wing on us and fly. In practice, the how was here. In practice, we got there by building these jet planes that essentially we are flying, right? So my point is that predicting a future is not, the tools that we will use is not always easy. They're not always easy. Give you another example. The people were saying that someday we will be able to build such a powerful binocular that you can stand in Los Angeles and see New York. The thinking was that the how was this huge telescope that would allow us to see the other side of the continent. Well, that didn't happen that way, but we are doing that. How? Well, we got FaceTime, right? Yes, we can stand in New York and have FaceTime with someone in Los Angeles and can see that. So my point is that it's good to have some idea what it is that we want to do, but don't be completely sold on the how, because there are things that emerge, technology that emerge, and that can help us. But our goal is that the what part is the one that we know what we want in the future. We want this curve to be straight like this or nearly so, rather than what we are doing here. But how we get there, well, there are some tools that we are developing here and there, but you may be surprised that others may show up. The how part is the one that we have to look at the technology. We have to not be afraid to try different things. And could there be a big bang adoption of all of these? Well, maybe, I don't know. Can't tell. But we do, from history we know. From history we know that there was a time that fiber reinforced polymers were purely used for military applications. Very expensive. They were not practical to be used in civil engineering. We know that, right? But now they are quite competitive. It can be used. So there's hope that these technologies that they seem to be far off, someday they may be acceptable. In fact, the new project that I received from Federal Highway Administration is looking at copper-based shape memoryallo and iron-based shape memoryallo because they're more cost-effective. See if we can get them to a point that can be used in a bridge somewhere in the West in high seismic areas. So there's hope. Now, we human beings like to dream, right? So in the car industry, you have these concept cars. I'm sure you have seen them. Many of them don't even get built, right? That's a concept car. It charges the profession, the field, gives a sense of mission that this is where we're going, right? So yeah, this was a concept car at some point. And but now I have one in my garage. So it did materialize. Some of these concept cars materials. Well, if you're doing that with cars, why not the concept bridge? Concept bridge. I was having breakfast with a colleague talking about the environment and how our role can be. Well, the issue is that we're wasting a lot of material. What if we design our bridges so they can be deconstructed and reused somewhere else? And the reason I'm saying that, you know about AFC report cards and deficient bridges in the US. About 11% of the US bridges that are considered to be deficient is not because of their structural condition. It's because of their function. So if these bridges, then they're in good shape. Structurally, they're in good shape. If they were built so that they can be disassembled and used somewhere else where they could serve the function, you could be saving a lot of material potentially. So that's the idea. This resilient design for deconstruction, this terminology designed for deconstruction, I'm borrowing it from architects, the DFD, they call it. So the whole idea is that, well, can we build something that's resilient and also it can be deconstructed. So this is the idea. So this is the plastic hinge element that is resilient. could use a variety of innovative material, so it can work well. And the upper part of the column is designed so that it remains elastic. So all the plasticity will take place in the pre-assigned plastic hinge. So these are some samples where the plastic hinge here, we have a ECC and shape memory alloy. That's the plastic hinge element. This one has rubber, and again, the shape memory alloys. The upper part, we have used composite filled with concrete to remain elastic. This was something that the university convinced me that I should patent it, so we did. And but then we built several columns. After testing several columns and having confidence that this works, we implemented that in a bridge model, in a two-span bridge model, about 62 feet wide, 62 feet long. And this is how the pieces came together. A graduate student prepared this and obviously was fascinated by this design, so took his time making the video. So these are all the individual pieces, and then they come together. Then you have the cap beams and the superstructure, and there are these extra weights that you put on the model for our shake tables simulation that you need to use. And of course, all of these can be disassembled afterward. Let's see if I can go to the next one. So we built this model, and this was the National Science Foundation project, and we tested this up to 6%. Again, remember, this was supposed to be deconstructible. That means you build it, put it together, put an earthquake on it, relatively strong earthquake, but go back and disassemble it and reuse it. So that was the idea. So this was the first run. We went to 6% drift. Certainly, the bridge did not collapse. These steel trusses that you see here, those are our catch system in case something goes wrong and the bridge does collapse. We don't want our shake tables to be damaged. So looking from the top, again, large displacement. This is a strong earthquake that we applied. So we did that, and then we disassembled it. After undergoing all that deformation, we disassembled. This is the one that has a ECC and shape memory alloy in the plastic hinge. There's some surface cracks for sure that are repairable. The element that had rubber, the column that had rubber, there's no damage at all. The top connections, we use what's called a piping connection, no damage at all. And these are the shape memory alloy bars that we recovered. So we disassembled this and put it back together and retested that. This time we went to very large drift and until failure. So it worked. This process, this concept worked. So what is it that we learned? We have learned. It is possible to have resilient bridges, but we need to get away from our comfort zone of conventional steel and conventional concrete. There are barriers, no question about it. The initial cost may be higher, and you have to be able to convince those progressive engineers that I mentioned that they exist. The evidence is there. That, yeah, don't just think about the initial cost, maybe 4 or 5% extra cost. With nickel titanium, that's extra cost. With copper, we are hoping to reduce that to down to 2% possibly. But look at life cycle cost. The fact that you don't have to repair the bridge, you don't have to replace the bridge, you should factor that in. And we need to develop design guidelines. We have design guidelines, we have preliminary design guidelines, but the database behind those design guidelines is a lot less populated than what we have for conventional concrete. Okay, so we have to realize that we need to do that. Now, I think someone was talking to me that, yeah, they're materials engineers. Yeah, we got to talk to them. Structural engineers, civil engineers, need to talk to materials engineers. And I'm not just talking about construction materials, okay? Get out of our comfort zone. Talk to other people. You may not understand each other's language, jargons. I know that. I've dealt with that. Dealing with composite people, shape memoryallo people. But it was exciting to be able to get over those barriers. So we do need more studies, but I'm saying that, well, it's okay to begin to adopt these technologies and learn from the field application, as well as, of course, we have to do a lot better job in constitutive models and the analytical studies to understand these better and gradually end up with great resilient bridges. This is my last slide. I'll be happy to answer any questions. Professor Shi, yes.
Very interesting presentation, very intriguing. Thank you.
Thank you.
So when it comes to the comparison between USBC and PCC,
Yes.
especially dealing with the seismic settings, what's your opinion? Like when should we switch?
I would, USBC, because of its very high strength, it can be a problem actually. And again, lots of projects. In one project, we did that in a 2-column bend. In one column, we put ECC. In another one, we put UHPC. The ECC strength, we controlled it to about 6 KSI. UHPC was over 20, okay? Because of that high strength of UHPC, the damage extended into the connection. Whereas with the ECC one, no, it was within the column. And we don't want damage in the connection. So we have to be careful about when and where we use UHPC. Then sometimes the more is not the better. Yes, please.
Very nice presentation.
Thank you.
Not my field necessary. But first, I want to make a comment. Then I have a couple of minor questions. First comment, I keep hearing the plastic case, but should we really call it a plastic? It's not perfectly symmetric. It still is not in each direction.
Yeah.
The same. It's not a real plastic edge in the mechanics sense, because it doesn't continue to rotate.
It falls apart eventually, yes.
Right.
Well, you're correct, but these are our jargons. That's we use. Let me give you very bad news, and probably a lot of you know about that. How many times a day do we say okay? All of us say that, right? We're very agreeable people who say okay. So what's behind okay? You know that? You know that? No. What is behind? Where the letter O and the letter K? Where did they come from? From military person. And so then you know more about that story. Well, the story I heard was that this person didn't know how to write. So wanted to say all correct. So all, he spelled that with O, and correct, he spelled that with K. So that's why we say okay, but it's totally wrong, right? So, jargon.
Okay, then just two curiosity. The first one is you've shown different ways to deal with the plastic. One was, for example, even as part of the material in a limited area.
Yes.
So, do you see any problem in the bond with without the bond or
Not really, because first of all, when you put the ECC, you don't smooth it. You just have rough surface and the rest of the column, the concrete, that's not an issue. And also, I mean, let me extend your question to when you use PCC Memorial, they have smooth surface. So the bond between ECC and smooth surface is not very strong, but that's a plus. That's a plus side because all the anchorage is done outside the plastic hinge with steel bars and couples. Within the plastic hinge, the lack of high bond strength between ECC and SMA means that yielding can spread over the length and give you a better ductility.
The second curiosity is the last example.
Yeah.
Just one is, do you see any potential problems in the factor of cycle? You showed me the loading the ship.
Yes.
If you guys also test the ship, it will be out of phase and so on before you
Not really. Essentially, what we are doing, we are mimicking what we do in conventional construction. You know, with these connections, these couplers, they're very strong, and they work very well. Okay, the kind of couplers we use. There's another project, you know, that was about accelerated bridge construction, where we evaluated several different types of couplers. Some other couplers, especially when they're bulky and large, sometimes they're vulnerable. Okay, but you don't want to use them for this kind of application anyway. Yeah, sure.
I just took a picture.
To the picture.
Design for deconstruction.
Yes.
Send it number to my son, he's a professional. Say,
Okay. Yeah. Yeah.
I think the concept that really was is the design for deconstruction.
Yes.
That's a very good philosophy. But in order to kind of deconstruct it, easy to deconstruct. Then typically that joints.
Exactly. Yes, absolutely.
You say that plastic or whatever it is, right?
Yeah.
But do you think that for the kind of decrease, the resilience of any of the structure?
That's a very important point, that the connections have to be right. Okay, because that's the most critical part of the structure, bridges or buildings under seismic loading or lateral loading. That's why you really have to do a careful job, have to evaluate it, look at all the options. This is really something in infancy. We have a lot more work to do before we streamline it, make it easier to construct and reliable. What we did use, they are certainly reliable because the connection, the couplers we use, these are proven couplers. But you may say, well, maybe there are other ways of doing that. Well, let me tell you, when I did this project, IKEA, everyone knows about IKEA products. They come in a box, right? And you just assemble them. And I looked at the connections that IKEA uses. See if we can bring those and adopt those in bridge engineering, all of that. And certainly didn't work because the scale was different. My point is that, sure, you start with familiar couplers, which we did, and they work well. But we should be open to use other types of connections. I worked with somebody whose field was physics, had PhD in physics, and with the specialty in shape memoryallo. He was a consultant in my project. And he said, yeah, these are, you have, this is super elastic material. So if you have let's say a ball, there's a bar, there's a ball, and get half sphere sort of thing, and get another bar and have a ball at the end, and you can push it in there. Because this is super elastic, it opens, grabs it, goes back, right? It doesn't yield. So, yeah, that could work, but I'm not willing to spend 3 years to say why not, if that's going to work. I'm going to stick with the conventional method and work on the conceptual aspect of this DFD at this point. But again, the door is open for to do a lot more work. Maybe try there, they can fund some projects. Yeah, maybe the next round. Yeah. Sure.
Excellent thought. I'm curious, like, for example, prefab cleaning construction,
Yeah.
like, start a while, like, it's a certain technology, but in the practice, like, it's still not widely used.
Oh, no.
So, what do you think, what are the medical rules?
What's the reason?
Yeah, reason, not being a
Because we just haven't thought about it. Okay. Look, in some ways, if you think about military, they build bridges that can be deconstructed. They do temporary bridges, right? Going someplace and temporarily, and there's a river, they build a bridge, and usually made out of steel and conventional bolts and nuts and all of that. They build it. After they're done, they undo it and they take it with them. So it's not a completely new idea, but has been used only for military application. We have 600,000 bridges in the US. It's a very, very new thinking, new concept. And really part of the reason I convinced the NSF reviewers was that about 9% of the CO2 emission in the world is coming from a single source. You know what that is? Cement factories. Single source CO2 emission. So it's, again, maybe a dream. I tell you what, the fact that we use that shape memory alloy and ECC was beyond my expectation. I didn't think I would live to see it applied, but there can be surprises.
Yeah, I'm seeing like, for example, a few projects we had demonstrated new material. Therefore, highly public projects always have liability issues. You say you try out new things that didn't work, who will be responsible?
You're taking a chance. You're taking a chance, but like any other engineering process, there's a risk. Okay, there's a risk. My older son is anti-vax. Okay, for this COVID thing, I'm not going to take the vaccine because it's not proven much. And my argument to him is that at some point you got to trust and move on. When you sit in your car and drive 80 miles an hour, you're trusting a whole bunch of people. The people who designed the car, the people who put the tires together, that made the tires, the civil engineers who built the road. You're trusting all of them, right? Is there a possibility of failure? Yes, there is. With COVID vaccine, so yeah, there is a risk. I understand that. But so going back to your question, yeah, that's every time you do something new, there's a risk. If you're not willing to take the risk, then what do we do? I mean, if human being did not want to take the risk, we would be living in caves. Maybe it's not such a bad thing, as long as you had good internet, good Wi-Fi. I'm sorry, you had a question.
You're describing you are in compliance with all of the clients so that you can actually adjust for the motion flow. And as a result, you're finding right additional motion. You actually have material mechanics. But as I understand it, my question was, how does this impact the surface? Because if you on the project?
Generally, no, unless you begin to have some failure in the supporting elements. But that's with this new novel material, because we don't have failure in the supporting elements, that's not an issue. For conventional construction, yeah, you could have settlement. In fact, that bridge that I showed you about success, quote unquote success, that bridge did settle in 1994 Northridge earthquake because of the failure of the columns. Of course, but they shut down that bridge to traffic and they tore it down, they rebuilt it anyways.
So the oscillation of the client.
Yeah.
The fact that they are flexible, it's not that matrix. They are mostly going sideways, are going to remain mostly.
Yes, exactly. No, that oscillation by itself is not an issue.
Okay. Yeah.
Yeah, thank you.